posição.
Okay, thank you very much for a great presentation. And we shall now move to the last presentation of this workshop where I have the video. So let me just share my screen, but we have almost all of the authors, I believe, in the call, so we can do a Q&A after.
Thanks. Other questions can send to our email.
Just a second. Okay, I hope everyone can see my screen.
Yes.
Does everyone see this on full screen? Or no? So let's
Yes,
do this.
I think so.
My name is José Eduardo, and I'm going to present my work named Fighting Underpriced DOS Attack in Ethereum with Machine Learning Techniques. Let's begin with a little introduction to the main subject, Ethereum. It is currently the second most large cryptocurrency in terms of market capitalization, with a value of more than $40 billion. In this chart, we have in the x-axis dates from October 4th to November 1st, and in the y-axis we have the market capitalization value. In Ethereum, we have two main interactions with the platform. One is the simple transfer of money between users, where they send Ethereum currency called Ether to another user. The other interaction involves smart contracts, which are decentralized applications that can be deployed over the Ethereum network. Those smart contracts use a language that is Turing complete, hence it disposes of a rich set of computational instructions. The presence of a large set of instructions makes Ethereum susceptible to a wide range of attacks. One of the threats is called the distributed denial of service and is usually abbreviated to DDoS. In this kind of attack, specifically in Ethereum, a user disposes of one or more wallets to interact with the platform. Then, it fires multiple transactions and smart contracts to the network, aiming to cause slowness. Given this introduction, let's talk briefly about the problem involved in this work. When a user sends a transaction or a smart contract to the network, he must provide a fee. Even though this protocol penalizes malicious users, Ethereum itself already suffered from this kind of attack. In this work, we analyze Ethereum under a specific kind of attack, called underpriced DOS attack. In this situation, attackers create several transactions and smart contracts containing low-value fees. This picture illustrates the establishment of this attack. One or more users disposing of multiple wallets create a large number of transactions and send it to the network. As a result, the queue of pending transactions named mempool gets flooded by many malicious transactions, concurring with honest transactions to be inserted in the blockchain. As the figure shows, malicious transactions tend to have a low-value fee, as honest transactions can contain a wide range of fee values. Given the problem of this work, I present you the objective of this work. Our first goal is to use quantitative research to understand Ethereum behavior under DOS attack and the periods of high demand. Finally, our last objective is to use machine learning techniques to identify the underpriced DOS attack. Given the objectives, I am now going to talk about the evaluation environment and methodology. To create the simulation of the attack, we propose an architecture of components. Our first step in this evaluation is to create a simulation of the Ethereum platform under three scenarios: a regular flow, period where underpriced DOS attack occurs, and the period that we call Ethereum boom, where a high number of users interact with the Ethereum network. First, we have a database containing the Ethereum transactions that will be inserted in each scenario. It will provide these information to the controller. The controller itself receives the transactions. This component concentrates all the logic in the simulation. First, the controller fires a signal to Ganache to initialize the instance. Ganache is a tool to easily deploy a local instance of Ethereum network. The Ganache then establishes the local Ethereum service. In this architecture, we also use a library called Web3py, which is a Python library to communicate with the Ethereum network. The controller uses it to perform requests and responses. In this way, the controller can record the current state of the blockchain in the database. The transactions present in the database are organized in two groups. Real transactions collected using the collect from Ethereum in our previous work, and a set of synthetic transactions to reproduce an attack to the Ethereum network. The synthetic transactions were configured with values presenting the real transactions, changing the gas price to 1 gigawatts to reduce the attack cost. The transactions appear in the real network in the 16th of May of 2019. With this evaluation environment and methodology, now I present the results of the simulation. This is a cumulative distribution function of the time that a network took to move from the mempool to the blockchain, which we have named here as pending time. There are three curves. The orange curve represents the regular flow. The blue curve represents the underpriced DDoS attack scenario. And in green there is the Ethereum boom simulation. The regular flow in orange presents the lowest pending time. In blue, we can observe the underpriced DOS attack. We note that 50% of the transactions took more than 50 seconds to join the blockchain, whereas the 50th percentile in the regular flow curve represents a pending time of 19 seconds. In the Ethereum boom scenario, the pending time is about 4 times larger, and in almost 50% of the transactions, we observe a pending time longer than 200 seconds. We also use the Kruskal-Wallis test to check the difference between the regular flow and the underpriced DOS attack scenarios. The test concludes that the curves are statistically different. These were the results of the experimentation. We are now going to talk about machine learning techniques. Given the great complexity of learning the characteristics of the attack by a person, the application of machine learning techniques was chosen to identify the problem. We used a wide range of classifiers, which are decision tree, random forest, KNN, SVM, naive Bayes, and a committee of classifiers with the aforementioned classifiers. We had used 2 different committees in this work, hard and soft. We have the hard committee, which is based on the majority voting, and the soft one, which is based on the certain that models have that the transaction belongs to a class, and then provides the answer based on an average. To evaluate these models, we dispose of the following metrics: accuracy, precision, recall, F1 score, F beta score, and AUC. As the data is not balanced between the classes, we use 3 different balancing techniques, which are undersampling, oversampling, and smooth. We also divided the data in 70% for training and 30% for testing. Given the techniques used in the machine learning, we are now going to talk about the evaluation of these techniques. In this table, we present our results. The column shows the metrics, and in the rows, we show the classifiers grouped by balancing technique. One can notice that the random forest presented the best metrics for accuracy, precision, F1 score, and true negative. The decision tree presented the best metrics for recall, F-beta score, true positive, and the UC. Despite of good metrics, both hard and soft committing did not present the best metric in any scenario. Now, we're going to present the conclusions. In this work, we propose an architecture to simulate the Ethereum network. With the results of the simulations, we could observe that the underpriced DOS attack increases the pending time of the transactions. And finally, one can notice that machine learning techniques are able to detect the underpriced DOS attack with reasonable performance. For future work, we intend to integrate and jointly validate our proposal with existing countermeasures to mitigate underpriced DOS attack in Ethereum. With this, I finish my presentation. I appreciate the attention. This is the email that you can contact us.
Okay. Great. So I thank the authors, of course, for the presentation. Are there any questions? I think should be able to answer some.
Anyone? I have a question. Can you maybe explain once more how the underprice attack works? Because there was this picture with the attacker and the many transactions and all this. But would this attacker take an honest transaction and split it up, or how does this work?
Oh yeah, can you hear me?
Yeah.
Yeah, a malicious user, it can be more than one, establishes one or more wallets in the Ethereum network, and it fires a lot of transactions with following the principle that it might be a low fee, and it goes in a short period, so the mempool gets flooded. That's the principle of the attack.
But if these many transactions have low fees, then they will sort of create the bottom part of the mempool, and the high fees will still be served, or not?
Yeah, the intention of the attack is to create a delay in the honest transactions, and in our simulations, it in fact it had an impact in the honest transactions, causing slowness in the network.
And why is this delay? Because the honest transactions also have low fees, or because the whole processing time increases, or?
The process time is the same, but miners can choose different transactions to mine based on the characteristics of its client. So it might mine a regular transaction or not. When the mempool is flooded, they concur with each other, and then you add this delay because the mempool is actually flooded with many transactions, honest and malicious transactions.
And how does that work? A miner will take a transaction, look at the fees, and then decide whether to use it or not.
Yeah,
is that how it works? Yeah.
This is very particular to the user. It can decide how he or she is going to mine, and there is not a consensus that there is a specific characteristic that informs how a miner is going to work. So we can't conclude anything from that. So they probably might just concur with others.
I see. Thank you.
Eduardo, could I ask a question about how you did the simulation? Thanks for the talk or the video talk. How did you do the simulation exactly? Did you actually run a real system, or what did you do?
Yes, I used Ganache. That is a tool to configure and fire Ethereum locally, and we collect transactions from the real Ethereum network to replicate in these three scenarios and to compare. But the scenarios were run in our laboratory, and the main helper in this is the Ganache to use the Ethereum, and we focus our business logics in our controller component.
Yeah, I understand. Thanks.
I also have a question. Thank you for the presentation, of course, for doing the video. So your DOS attack is based on many transactions, where you mentioned the transactions, like they're not expensive in terms of computational tasks or processing power. I know there's quite some research, or recently there was research, there's a great paper by Daniel Paris as well, on creating many low-cost transactions which are very expensive computationally, and how that can be used as an attack against the network. And so yeah, I was just curious whether you perhaps thought about looking into how to also detect these types of attacks.
To detect these attacks, we can use more features based on the input of the transactions and smart contracts to check. But there's an issue detecting this, because as you can see, regular uses of Ethereum network could also lend to slowness in the network. So the difficulty in this process is to identify what is a malicious and what is not.
True. Yep. Okay. Any other questions? Okay, I think I believe that concludes actually the SOCCA workshop 2020. I would like to thank all the speakers, presenters, and I believe, Katinka, that this was recorded, which I assume will be made publicly available. So if anyone wants to rewatch any talks, there will be information on where to access them.
Yes. So thanks, Sam, and thanks everybody for joining. Thanks for the presentations and for the submissions. And indeed, the workshop has been recorded, and I will have to talk to the performance people how they want to publish things. It always takes a little while to process these videos until they're ready. So that will take a bit. So thank you all for joining. And as I understood, performance will be in Milan again next year. So let's see whether we'll have another workshop next year and then eventually meet. Hopefully.
Great. Thank you very much.